And my slides will totally move forward soon. Okay, I'm also not an expert in the field of algorithms, and I'm not an expert in the ones I want to tell you about. But these are the algorithms I found totally cool when I went, hey, I'm going to be working with algorithms, and what cool stuff is existing, and so on. So I pulled the talk together out of the 10 algorithms out of probably a few hundred new ones that I found were really cool. And algorithms are cool. There are people whose job it is to just sit around and think up new ones, or to think up improvements to existing algorithms. And as far as I can tell, they don't come to our conferences because they've got their own special conferences where they do this thing. And they don't even seem to be solving, I've got this real world problem, how can I make it better? Except perhaps people doing things like PageRank algorithms for Google. They seem to be like, hey, you know, here's a graph and here's a graph, are they the same graph? How can we work that out? So they seem to be just focusing on how to push the envelope of what's possible. Theoretical mathematicians or theoretical physicists. And I want to go to their conferences because it sounds really cool. We, of course, then use those algorithms, eventually when they filter down to us, to get stuff done, to solve these real-world problems, or to create new problems that then will need new solutions. And let's think about that word, algorithm. Where does it come from? So here's a couple of possible roots. If you went, okay, where does algorithm come from? Pain, to be cold, kind of close, yeah. But it's actually not from either of them. The word algorithm is a Latinization of this guy's name, Muhammad ibn Musa al-Khwarizmi. This name actually appeared on a slide in a talk I was listening to yesterday, and I was like, aha, yes, someone else knows that this is, when Latinized, just pronounced algorithm, this last name, of course. A 9th century Arab scholar, and also the person we may as well say is the father of algebra, because he wrote his treatise on what we now consider to be algebra was what started that field, and probably essentially what you read when you were in high school. He wrote this wonderful piece here, and I'm not going to read it out for you because I know you can read faster than me. But the second last line here, and I'm not allowed to raise that arm, the second last line here, algebra, just means the word restoring. But that's where the word algebra, that you learned in high school, that's where it came from. And this word algebra, restoring, was in the title of his book, where he introduced the fundamental algebraic methods and techniques for solving equations and so on. I want to give you a quick idea of what he was talking about, something you'll recognize. So, quadratic equations. We are getting there. X squared plus 10x equals 39, solve for x. Now, we could just do the very simple one, plug in x equals 1, plug in x equals 2, plug in x equals 3, and so on. But we all know that in many of these situations, x is not a whole number, it's not an integer. But he gave us a really nice way of looking at how to solve this, called completing the square. You may know this already, but back then, this was a new idea. So we can make a square, this gives us x squared. And then we need to add some little extra bits to give us that plus 10x bit. So if we take 10 and we divide it by 4, and then we add the area of 4 of those, which then of course are 5x divided by 2, then the area of this space on the page here is 39. And then, of course, with completing the square being part of the name, we can add in those little bits in the corner. And each of those are 5 by 2 wide, they're little squares, so we know what those are. And so we have 39 plus 4 of 25 on 4 is 39 plus 25 is 64. The area of this whole square is 64. And we can use that to solve for x, and x is 3. And you can do this even if x is a non-integer number, of course. So he came up with this method of solving quadratic equations. I kind of wish I'd been taught this method in high school. It would have made understanding quadratic equations other than the parabola a little easier, but it's kind of neat. So, moving on, algorithms. Algorithms have two things we primarily need from them. Obviously, we need them to be correct, or at least close enough, and that's handy. And we want them to be fast because we're really impatient. Lots and lots of work goes into making them fast, and I'm just going to hand wave at order notation now. We have order notation. It gives us an idea of how complex and thus how long an algorithm will take to run. The further we go down this chart, the more awful the solution is. And we can see that quite well represented on a graph. We want something that at the very least scales fairly closely to the number of inputs that go in. That's usually the goal. So let's get into it. First, I want to talk about something that is an ancient idea. Definitely not created just this century, but something that has become increasingly useful this century. In 1854 in central London, central London had a cholera outbreak. We didn't have germ theory at that time, so people still thought you got sick by breathing in bad air. But one man, John Snow, but not that John Snow, interviewed the family members of people who had died. And he noticed that almost everybody who got sick had drunk water from a specific water pump. There were all the houses close to this specific water pump, and some other houses where they sought water from that pump on purpose because they thought it tasted better, or they sent their kids or their workplace, sent their kids to school near there, or their workplace was near this water pump. So he thought, but then there were some anomalies. There was a brewery just across the road that used that water, and the workers at the brewery got an allowance of beer, but they weren't getting sick because they boiled the water at the brewery. But there was no germ theory yet, so he hadn't really accounted for that anomaly. He was pretty sure, though, that it had something to do with this water pump. And he drew this map. He said, here are all of the people who have died from this cholera outbreak. So he argued for the pump to be disabled, and the local parish agreed, and they took the handle off the pump. And people had to go elsewhere to get their water. However, he acknowledged that people had also moved away from that area because bad air, and thus the cholera breakout was already backing off. We're pretty sure these days that he was correct, because we now know that cholera is transmitted by diseased water sources. So, Voronoi diagrams. This was the most primitive and original type. But you take a thing, I've got a bunch of scattered points. How do I project usage? When faced with a largely equivalent service of water, a supermarket, a barbecue, most people will pick the one that is closest to them. This means so long as we can make intelligent guesses about what closest means, taking into account that people travel, go to jobs, have friends, etc., we can predict catchment areas. And we came up with Voronoi diagrams, this one thing here. This was by Russian and Ukrainian mathematician Grigory Fedorovich Voronoi in 1908. And each colored space is a representation of all the parts of that diagram that are closest to the black point inside it. Now this is great because you can think about, okay, I've got a supermarket, to take Australia where we have the two large supermarkets, Woolworths and Coles. Here are all of my supermarkets scattered on a graph. These are the people who are most likely to go to them, overlay in a different way the competitor's supermarket. Where could we put our next supermarket to be most disruptive to our competitor's supermarket without being disruptive to ours? How can we steal more market share? But they're also useful in a whole bunch of other things. Helping model and handle the capacity of a wireless network, because people's devices will connect to the closest network point. shattering and fracturing and faking lava textures for games, that's always cool. Robot navigation, it will go to the closest thing. And the one I liked best, mouse hover state. What icon is this mouse pointer closest to? Because people aren't very exact. They just want to like hit that space and have it move and work. They're used in biology and hydrology and chemistry and physics and ecology and computational fluid dynamics and health and engineering, et cetera, et cetera. These have become insanely useful. And there are a whole bunch of fields which are using slightly different variations on them, but there's one good algorithm that does it. I'd love to go into the details of the algorithm, but it took me an hour and a half to understand it, and I want to cover some more in this talk. So I'm pretty much going to do that for all of these. I'm going to say, there's this cool algorithm. You should go and learn more. So these are things you'll come across with them in our fields. Fourier transforms. Again, not a super new tech, but something that we have come up with cool stuff with related to. So a Fourier transform decomposes a function of time into the frequencies that make it up. In a similar way to a musical chord can be broken up into the frequencies that make up that chord. Linear operations performed in one dimension have a corresponding operation in the other domain, and sometimes it's easier to perform those. So let's have a look. Oh, a slightly easier way of phrasing it in a non-math speak. A method of processing an irregular signal, such as the voltage fluctuations in the wire that connects to an MP3 player to a loudspeaker. And this is great. You might be thinking signaling processing, and that's what Fourier transforms are used for. So I've got this GIF, which is already partway through, which is a bit of an awkward thing. It'll start again in just a moment. So the red one is our function. The next graph that we're going to get as soon as this starts restarting. There we go. So yes, here is our function. It is made up of a bunch of frequencies. We can create the component frequencies. We add these together and we get something that's fairly close. Really handy when you have to deal with zeros and ones. We can shift that to consider all of the individual frequencies that are components, and we can see that the height of those frequencies change. So we've got one that mostly contributes, and then we add little extra bits to it. And that's essentially what this is about. So Fourier transforms are used in all of these kind of things. Let's look at the data compression one. An 8 by 8 block of pixels can be thought of as a 64 sample signal. A tiny little set of this can be considered as individually 64 signals, and thus the sum of 64 different frequencies. Empirical studies show that on average, 57 of those frequencies can be discarded, and we still don't lose much image quality. So Fourier transforms allow us to determine which of the frequencies we can get rid of. And that's the short version of those. Calculating these naively is order n squared. Calculating them fast, which again is an old-ish algorithm, is n log n, so much better. And this came about because we realized we could calculate Fourier transforms on the fly. Recently, just a few years ago in 2012, it was discovered that, or considered that signals with Fourier transforms include a relatively small number of heavily weighted frequencies, are called sparse. And this algorithm determines the weights of the signal's most heavily weighted frequencies. The sparser the signal, the greater the speed up the algorithm provides. So as of 2012, we've been able to calculate Fourier transforms 10 times faster, which is really cool. If the signal is sparse enough, the algorithm can sample it randomly, rather than reading it in its entirety. That's kind of cool. To get them at maximum speed up, you divide the spectrum into small enough bands that you only have one heavily weighted frequency per slice. And as I said, with care, have to care about the care, we can have a 10 times speed increase. Otherwise, we can make it based on that k there, which is the number of non-zero coefficients in the Fourier set. And n is, of course, the number of frequencies. So something cool happened. We can do this faster. And of course, if we can do this faster, we can do even more compression faster. We can do a whole bunch of things. We could potentially compress data sufficiently fast on the fly that you can download a high-quality movie and watch it on your phone without having to worry about buffering. And in fact, that's what this has already been used for. So Netflix and Stan and all of those are using the nearly optimal sparse Fourier transforms to help get your compressed data to your devices faster so you don't have to worry about buffering. Singular value composition, this is the last old one I'm going to talk about, but I just did want to say, this is the factorization of a real or complex matrix. So basically, if we start with the top left here, that's our original matrix or vector. There are different ways we can consider this. And we apply some function to it, m, to get the distorted one on the right-hand side. That's essentially what we can do. But singular value decomposition allows us to work out how to create m by using a bunch of vectors. So we can do a rotational shift, and then a transformation, and then another rotational shift to get to the same thing. In doing so, we can, if we factorize matrix shifts across we can factorize matrix shifts across multiple initial conditions. This means we can reapply them as necessary, but we can apply them to other inputs as well. Now, this I thought, okay, that's kind of neat. Nice to know how to do that. I did some sort of transforms back in high school and university. How is this useful? Well, it's super useful. If we can compare, so we can use this, we can compare the structure of molecules. We can find out, is this molecule a left-hand version of that molecule? What is similar, what is different? What if we rotate it? We can do that. It allows us to do genomic signal processing, it's pattern recognition. If we want to do pattern recognition, then we have to remember all of the bits of the decomposition, but that's okay, it works out fine. And unsurprisingly, what I was very excited by, it allows us to do numerical weather prediction because it allows us to do ensemble forecasts. You take your transform, you're like, this happens, and then that happens, and then you're like, what if we just twiddle the initial conditions, and we take the transform, and we do it again? And you can undo them, and it's great. So cool, lots of fun stuff. Okay, new stuff. Old concept, new stuff to come. Evolutionary algorithms are a form of artificial intelligence or machine learning. There's all sorts of terms here that don't quite fit. Inspired by biological evolution, such as reproduction or mutation, recombination or selection. Candidate solutions to the optimization problem play roles as agents, and we pretend that they are bees and ants and creatures and so on. We have a fitness function that it tells us, is this good enough? So typically our solution is, I want to get a maxima or a minima. I want to be able to minimize the costs of making this widget, taking into account all of the costly inputs and the time taken and the labor required, and get a best price for it to go out, and it needs to be fast and all those kind of things. Or I want to find the best signal that I can get from this antenna, given that it needs to be lightweight and small and fit inside a case and all those kind of things. And there might be weight requirements, and there's definitely going to be a specific radio signal we want to pick up, and it might be in a noisy environment. When you've got lots and lots of inputs and things, it can be very hard for a human to come up with an algorithm that will give you the best solution. But you can throw it at one of these optimization things and just say, give me a maxima or a minima. Give me the thing I'm looking for, and maybe it's not the absolute best one, but it will do. Or maybe find as many of the maximas as you can. So genetic algorithms are a particular form of the evolutionary algorithms. They're predicated on the idea of survival of the fittest and natural selection. Typically, we start with a group of agents, and they compete with each other on fitness criteria. Think seeking food. And then they swap information, i.e. they breed, for the next round. The weakest ones are thrown out and replaced with random-ish variations caused by the breeding of the others. And even just some fully randomized ones as well, because that helps too. Now, setting up the fitness criteria and initial conditions for genetic algorithms, or for all of the ones that I'm going to talk about in this section, is as much art as it is science. So that can be the hard bit. And sometimes they give really interesting results. If you've ever played with boxcars, it's a lot of fun. The idea is that it uses genetic algorithms to try to come up with a vehicle that can go over a somewhat randomized created terrain. This one is the little boxcar that could. It doesn't really look like it would get anywhere at all. A lot of them fall over and don't get anywhere. Literally, they fall on the two pointy bits, and then they get stuck and it restarts. And sometimes they get a long way and you're like, go little boxcar, go! And sometimes it doesn't. Most of the time it doesn't. Sooner or later they all peter out. So, sometimes we get weird results. This is just fun. It's not doing anything interesting. And sometimes we get amazing results. This is a tiny little antenna, and it had to be tiny. Yet it is of the maximal power and accuracy given the constraints of weight and size and materials and such placed upon it. NASA created this, and it just threw genetic algorithms at it and said, go, make me a better antenna shape. And it looks like someone sat on it. But it works. It's a lot better than the spiral ones that humans came up with and the zigzag ones that humans came up with, and even better than rabbit ears. It worked. So, sometimes genetic algorithms give us great optimizations. And there's a bunch of these different types. The whole concept of genetic algorithms has splintered, so I'm going to tell you about some other. So artificial immune systems. They emerged in the 1990s. Didn't really hit industry until this century, so it totally counts. And they apply theoretical immunological models to machine learning and automated problem solving. And there are a bunch of artificial immune system algorithms. There's like 10 or so. I'm going to talk about the colonal model. There are others. This involves the selection of antibodies, i.e. candidate solutions, based on affinity, either by matching against an antigen pattern or an evaluation of a pattern based on a cost function. Kind of like what our immune systems do. The antibodies are selected based on their affinity, how successful they are at their job, and the resultant set competes with the existing antibody population for membership in the next generation. Same kind of thing that you'd expect. Low affinity members, ones that are not very successful, are replaced by randomly generated antibodies. Pattern recognition, because this can be used for pattern recognition, includes, of course, remembering the patterns that were matched, and that gives you your immune system's ability to match new viruses. And once you've got that whole set of all the patterns that it matched, then that's the solution to the problem of the pattern matching, if that's the path you go down. Now, it probably won't surprise you at all that this is useful in computer security. If you can create an algorithm that can evolve and change over time and correctly identifies when things are going wrong, when people are misbehaving, when non-usual behavior is detected, especially things that you have maybe given a fitness criteria for determining are harmful, then yay, computer security. Lots of fun there. Obviously, pattern recognition, as I mentioned, classification, very similar to pattern matching, and of course, optimization. So artificial immune systems gives you this wonderful algorithm that's focused on doing the things that are essentially our job. And I also want to talk about swarm algorithms. These are modeled on the behavior of swarming creatures. Bees and ants and wasps and termites and bacteria and even birds. Consider an algorithm based on bees. The bees go out to various places in their environment. When I say bees, think agents, but it's much more fun when I say bees. The bees go out to the various places in their environment and they say, is there any pollen here? And if there's pollen, hooray, they have information. They go back to the hive and they say, I found this much pollen. And all the other bees say, I found more and less pollen. And if a bee hears of somewhere that found more pollen than they found, then in the next iteration, they're going to go back to that spot. So you get bees going, randomly picking places that had more pollen than they had, and then from that original spot, they go somewhere nearby. And if the place that they go nearby has even more pollen than the place that they went to start with, pollen, nectar, one of these things, if it has even more of the stuff that they want, when they go back to the hive, they'll report on the new place. But if it doesn't, they'll report on the old place. And then again, bees that found somewhere that had even more nectar and pollen will be the places that the bees go to next. And you keep going and you get this distributed exploration across the maxima of your, or minima, because you can reverse the whole thing, across your solution space. And maybe you won't find all of the maxima or minima, but you'll find a lot of them. And they will converge on a consensus of this one is the best, or these ones are the best. Now, a little bit more on swarms. Swarms can achieve things that individuals cannot. This is what makes them different, and in some ways, for some problems, better than genetic algorithms. Rather than a single organism trying to do something, a swarm allows us to create massive things. And humans behave very much like both swarms and individuals. All evidence suggests that swarms have no central control. There are only simple rules for each individual. Go out, find out how much pollen there is, come back and tell us about it. And they give us emergent phenomena. And of course, they're self-organized. Each of the individuals knows exactly what it's doing. It could just come back and repeat the correct behavior. And they're really useful in all sorts of things. Data mining, locating cancer, that's a fun one. Simulating crowds, definitely good for simulating how humans will behave. And solving systems of nonlinear equations. And bizarrely, I was a bit surprised by this last one, airlines cruise scheduling. Because you can send them out and you can say essentially, what is the most efficient solution to this problem? Nominally send your swarms out to solve all of the potential variable solutions and emerge on a solution that is best. Interestingly, here are some of the things that they are currently being researched to solve. Traveling salesperson problem. I'm sure you're all familiar with this. I don't think we're going to find a one-size-fits-all solution, but we can find really good solutions for all sorts of various constraints using swarm algorithms, because we're essentially trying to solve the whole thing in parallel, which is what quantum computers would allow us to do anyway. Controlling unmanned vehicles, that might make sense, particularly driverless cars. If they act as a swarm and they take some of the things that swarms have, like don't crash into each other, speed up your velocity to match the velocity of the other vehicles around you, move inwards. Those are the kinds of things that happens in swarms. If you ever watch a flock of birds or getting together and such, you can see these behaviors emerge. That'll be useful for unmanned cars. And of course, programming nanobots, when we have them, for cancer-destroying missions. So we can use the idea of swarming to detect and identify cancer. We're just waiting for the tech to have the nanobots to fight them. So I wanted to talk about a couple of specific instances of swarming algorithms, because bees are cool. Although I'm not going to talk about bees at all, actually. But bees are cool. So first of all, there's the bacterial foraging optimization. So bacteria perceive the direction to food based on gradients of chemicals in their environment. They can attract or repel other bacteria based on the pheromones and other chemicals that they release. They can move around. They can do it somewhat chaotically by tumbling and spinning, and they can do it purposefully by swimming. It's not really swimming as we can think of swimming, but bacteria can swim. And if we treat them like agents and we consider their perception of food and other cells as a motivation to move, and they can move, then cells may swarm to a food source. And they may aggressively repel or ignore each other. I guess it's probably less aggressive if they're ignoring each other. So the information processing for this algorithm is, once again, to allow cells to collectively swarm towards optima. You use that as the fitness criteria. You achieve this by giving them a bunch of simulated cells, and you just look at the costs. If there's enough food, the bacteria don't try to repel each other. If there's not enough food, then they do, because they're greedy, which is good. So you'll find if this is like a medium-sized minima or maxima, and then like, you know, your larger maximas, they'll swarm to those. And again, like many of the algorithms, you just pick the ones that get the best results. And you randomly yank out some and throw them away because they're not as good. This has been used very effectively in noise reduction. I'm not exactly sure how, because I couldn't find that paper, but this particular algorithm has been very, very effective in all of these three. And there's a different type of swarming algorithm, is frog leaping, specifically shuffled frog leaping. The shuffled is very important. So this mimics the behavior of frogs looking for food. Not bacteria now, frogs. Frogs have eyes. That does make these things a little bit different. So they will watch what other frogs are doing. So you imagine the idea of you've got a bunch of rocks in the pond and you've randomly distributed food on those rocks, and the frogs want to get out of the water, onto the rocks, and eat the food. If a frog sees that lots of frogs are swarming to a particular rock and then leaving it, and it looks like they left it because there wasn't enough food there, the frog will go to a different rock. And if the frog sees that lots of frogs are swarming to that rock and staying there, and they're not fighting each other and whatnot, then there must be lots of food there. So this is how you detect your maxima and your minima. Well, reverse your minima. And then, of course, to make sure that you find all of the maxima that you're looking for, you randomly redistribute the frogs from time to time. And you can substitute in new frogs because they learn, and sometimes you don't want ones that have learned the things. You want them to go over and explore that part of the frog pond rather than beeline back to the place that they had already learned. Compared with genetic algorithms, the experimental results in terms of the likelihood of convergence to a global optimum and the solution speed suggest that the shuffled frog leaping algorithm can be an effective tool for combinatorial optimization problems. And in fact, they've been used in all of these. So this works well in water resource distribution, multiple user detection and communication systems, and so on, web document classification, and 0-1 knapsack problems. You all know the knapsack problem. I've got a bunch of awesome loot that I want to take back to the town and sell so that I have more money in my game, but I only have a fixed number of slots that I can put it in, and slightly more like the real world, things have bulk and weight. How do I most effectively fill my knapsack so that I can carry out the most amount of loot? No magic bags where you can stuff infinite amounts of things into them. A suit of armor is heavier than like a ring, unlike some of your computer games. So we can use the frog leaping algorithm to solve this. That's cool. And we can also solve other tightly constrained combinatorial optimization problems. This next one I thought was interesting. Teaching learning-based optimizations. I was like, oh, what's this one? This is not a swarm algorithm. Not exactly. This is based on an ideal world where school actually is what our parents think it was and not what we experienced. So you go into your class nominally, the teacher knows more than the students, the teacher teaches stuff to the students to increase their mean knowledge. And then the students talk amongst themselves with the goal of teaching the other students, to increase the mean knowledge of the other students. So you can think about this, you've got a group of agents, so the teacher has the highest fitness criteria, the teacher agent says, here are all of my settings, essentially, and the algorithms go, what if I took that one? If I take that one, then my solution to the fitness criteria is higher, then I'll keep it. If it's not, then I throw it away. And they don't take all of them, because otherwise you just end up with a bunch of clones. And likewise, when they talk amongst themselves, the students, you have a higher, more successful student talking to a less successful student. Hopefully the end result will be one that doesn't change and one that is closer to the mean, or closer to the solution. Teacher phrases, learning phrases, all those kind of things. And then you just go back and around. And of course the teacher isn't magical. The teacher is just the one that has the highest fitness criteria. And it's proven exceptionally useful at solving multi-objective optimization problems. In particular, these are some of the problems that it was applied to. How do we manufacture the tolerances, how do we manufacture within tolerances an overrunning clutch assembly? There are a whole bunch of things we want to optimize here. Size and weight and obviously correct behavior. And the teacher learning optimization problem beat the shuffled frog algorithm easily. It beat most of the swarming algorithms easily. It was better than all the genetic algorithms it was thrown at for these three problems. So each of these have slightly different domains that they solve better than the others. I'm not sure what a helical spring is, by the way. I looked it up and I went, I don't know. It'll be fine. But it did solve all of these three best. Now, I just want to throw out this one. As an alternative to evolutionary algorithms, you can get humans to solve your problems for fun. Crowdsourcing can be insanely effective because we kind of act like swarms as well. Don't know if you've heard of this, but Foldit is pretty cool. It allows people to gamify solving science problems. People join the communities and learn a whole bunch about biochemistry and how to fold proteins and how they fold themselves. And then they put it to use solving problems we haven't solved yet, even with genetic algorithms. Crowdsourcing found the molecular structure of a retrovirus before the scientists were able to. And that was in 2011. And then last year, there was a competition between scientists, a bunch of universities doing various forms of evolutionary algorithms, and the people on Foldit trying to determine the shape of a particular protein. And the crowd-sourced folk were faster. And all the scientists are like, this is insane. Like, these people just come along and they're like, we're going to learn how to do biochemistry in our heads and on our computers and stuff, and then throw our solutions at problems and see what happens, see what falls out. So when it works, it works. And when it doesn't, it takes a few, it takes a little bit more. And the last thing I want to talk about is graph isomorphism. This is a graph one. Graph isomorphism is the question of, here is a graph and here is a graph. They have the same number of nodes. They have the same number of edges. Are they the same graph? In this case, these two are the same graph. They're just represented differently. It's actually very easy, if you think something is the same, to say, are these the same? The computation required for that is pretty easy, yes or no. But it's actually hard to say, given two graphs, can you calculate for certain, as a single algorithm, are these the same? And we haven't been able to solve this. So it's easy to verify, but it is hard to solve, or at least has been. Last year, Laszlo Babai announced that he had an algorithm to solve this in quasi-polynomial time. And then a couple of weeks ago, just this year, he was told, hang on, no, it doesn't solve this case here, therefore it's not a full solution. And he thought really hard about it, and he solved that quibble. And like previously it was announced as probably quasi-polynomial time because of this little uncertainty about this thing that he hadn't quite fully knotted out. They threw back some failures to match. He came up with a solution to solve that. And now he has solved that as of about a week ago. he has an algorithm that he says can solve this in quasi-polynomial time. So quasi-polynomial time, for those who aren't familiar, are algorithms that run slower than polynomial time, but not as slow as exponential time. And this is wonderful because it's made a whole bunch of people who thought this problem, the answer to the next question was done, dusted, and unfortunate, have gone, hang on, if that's the case, maybe. Can every problem that can be easily verified be easily solved? The answer might be yes. As I said, there's a bunch of people who are like, nope, well, we can't solve that one, so we can't solve any of them. Not quite, but you know. And now they're like, actually, maybe yes. Maybe we just haven't found the solutions yet. And that's incredibly exciting. And as I said, that was just last week. So thank you.